Probably wait till five after or so. How do, Andy?
Hi Ryan, how are you?
Oh, I'm doing pretty well. How are things going with the research?
Research are progressing.
Hmm,
Thank
That's
you
good.
for asking.
Are you on schedule?
Yes, I've been writing my proposal. Hope to finish it up soon and defend it.
Awesome. When is your defense? I'll sit in.
Oh, that's a defense still next year, but the proposal maybe next month.
Oh, okay.
Mm. Good luck for the talk anyway.
Thank you. Yeah, people are starting to file in. All right. We're gonna start this at five after, everybody. Okay, well, I want to keep everybody's time, so I think I'll get started if other people join in, that's fine. Uh, okay, well, good afternoon, everybody. Thank you for joining. My name is Ryan O'Connell. I work for Kilduff Underground Engineering. We're a smaller design consulting firm specializing in tunnel and trenchless construction. We have two offices here in Denver, where I am, and then also out in New Jersey, close to New York. What we're going to be talking about today is pipe canopy pre-support with sequential excavation method tunneling under active roadway and rail tracks. And I'm sure some of you have noticed that this is an RETC presentation. I gave this there back in June in Boston and was asked to present it. So I thought I'd just keep it exactly the same. So today we'll quickly go over tunneling basics. I'm assuming most people here are familiar with that. And then we'll get into the pipe canopy concept, what its applications are, and design considerations you need to have in your back pocket while designing a pipe canopy support system. And then we'll look at two case study projects, the North Temple Tunnel and the Mapleton Trail Tunnel that I've been a part of while here at Kilduff, and then any conclusions we can make. So very quickly, tunneling basics. There's a lot of common risks, ground loss at the face, support system failure, ground heaving, over excavation around the initial liner. That photo on the right is, the worst possible case of what can go wrong. And pre-support methods such as pipe canopies is one way to help prevent a lot of these issues from creeping up during excavation and your initial support design, or excuse me, installation. So the pipe canopy concept, it's a rigid tunnel pre-support system. It's typically comprised of steel tubes or steel with concrete inside casings that are installed out in front of the face. So there's a photo there on the right-hand side that you can see where they're all installed pre-support. So it's installed prior to the excavation, and you can form just about any geometry with this pipe canopy concept. With the steel tubes could be interlocked or there could be spacing between them. And we're going to see both cases here later on. So where did it come from exactly? It's derived from the mining industry with forepoling. As they're extending a drift in a mine, they would forepole or spile out in front. And this is kind of taking that concept and putting us on our own spin on it, where instead of forepoling as you go along, you just do it once from the beginning of the tunnel. And then you have your forepoles or your spiles all the way along the entire tunnel alignment. So because of that, there are limitations to the length that you can go with pipe canopies. But you can couple that with the sequential excavation method, like, for example, in that figure on the right, and do large diameter tunnel designs. And pipe canopies, some are familiar here in the States, but as you can see, being the green sliver on this pie chart, it's very rarely done in North America. It's mainly done in Asia and a bit in Europe, especially Western Europe. And the main reason for that is that's just technical know-how. Contractors have the equipment in their yard to be able to design and install tunnel pipe canopies. The designers in Asia have done them before. They know what to do. So it's more of just you do what you know, and you know what you know. So we're trying to push for more pipe canopy tunnels here in the States, especially where we think it's applicable. And where it's applicable is essentially when a couple of different conditions all come together. The first being that it's a low cover crossing where you have low tolerance for ground movement. So typically you want at least two diameters or 2D from the crown of your tunnel to the surface. That's just kind of the industry standard. Well, that's not always possible based off of the tunnel, the alignment of the tunnel. And if you are less than 2D, especially 1D or less from the crown of your tunnel to the surface, pipe canopy is a great option to use that pre-support system. So going in underneath railroads, airport runways, pedestrian tunnels underneath streets, those are all great applications of a pipe canopy system. And then also you can do any geometry with the pipe canopies. You get to install the tubes however way you want. So you can do any sort of non-circular geometry where otherwise you need to if you're using a mechanized tunneling technology. You also can do pipe canopies under the groundwater table. All the photos I've been showing have been above, but it's considered as a horizontal cofferdam where you install the steel tubes and they interlock together. You can see that piece that had been welded to the top of the pipe, the figure on the right. And they work fairly well. To install these tubes, these pipes, you need to use a slurry microtunneling system. Whereas when you're above the groundwater table, any of the trenches technologies to install these pipes are available to you. So the type of ground being the more adverse and the more challenging and the lower cover, a pipe canopy, pipe roof construction option is probably the way to go. or one of the few ways you can go. The more stable the ground conditions, circular geometry, or greater cover, you can use any of the traditional tunneling methods and the trenchless technologies or a tunnel boring machine for large diameter tunnels that we're all more accustomed to. And so we've already talked about geometry. The other thing I want to get back to is the length. And so the length of the pipe canopy pre-support method usually is restricted to about 400 feet. You can push it maybe to 500 feet, but really 400 feet or less. And the reason for that is because of limitations to the technologies that you're using to install the pipes themselves. So you're going to be using some sort of trenchless technology, be it an auger boring machine or a down the hole hammer or a pipe ram to install these pipes, and they have limitations in length due to the jacking forces and keeping these pipes in line and grade. There has been cases where they've used slurry microtunneling machines, and you can go as long as 1,500 meters, like in the case for that Hong Kong tunnel. So just going over an overview of what's the design outline, if you will, for a pipe canopy pre-support coupled with other tunneling methods. You start with designing your pipe roof. After that, you design the excavation and the initial support, and then finally your waterproofing and final liner and any other aperturances you need to install within the tunnel itself. And the pre-support for the pipe roof, or the pipe canopy, is really to provide ground stabilization before you even go to excavate within the tunnel perimeter. It gives additional stand-up time and support prior to installing the initial support. There are other considerations while designing this. What are the adverse ground conditions and the geometries, especially if there's low tolerances to settlement or movement or heave at the ground surface. Some sort of pre-support tunneling system, such as pipe canopies, is very advantageous. And then also, are you going to be using analytical solutions, numerical modeling? And in the case of both of the projects we're going to look at, and in most cases across the industry, you're going to do some sort of numerical modeling, be it 2D or 3D, to account for this pre-support system. So then initial lining that you install within the pipe canopy is just like any other tunnel initial lining. You could do steel sets, timber lagging or liner plates, shotcretes, lattice girders, any sort of SEM tunneling that you would do in soil. That's the same sort of initial support you would do. And that pipe canopy you can consider as part of that initial lining system, where they're coupled together, what you install during the excavation and the pre-support. And then you have your final lining you install, like other tunnels, cast in place, precast, liner, shotcrete with steel reinforcement if you have to install a waterproofing membrane, and so on. So project number one that we're going to look at, the first case study, is called the North Temple Tunnel. This is in downtown Salt Lake City. You can see the Capitol building actually out in the distance on the photo on the left. And this is going underneath North Temple Street, and it's connecting the Opera building, which you can see in the foreground there. You can see at the left-hand photo, you can see the tunnel. The Opera is that gray building, and then photo is taken from the Church of Latter-day Saints cathedral here, and it's going to connect the two buildings together so the clergymen and others don't have to walk along the street to get from one building to the other. It's 130 linear foot pedestrian tunnel, and it's 17 feet under the highly trafficked downtown roadway. The OD of the tunnel itself is 21 foot, and the final internal diameter is 17 and a half. So you can see it's less than 1D from the crown of the tunnel to the ground surface, which was part of the reason that necessitated that we use pipe canopy here. The other reason was the ground conditions themselves. We did 3 geotechnical borings within and along the alignment, and what we found was lots of gravel and cobbly soils and material along the crown, the upper half of the tunnel, and then more of lean clay to silty sand material down near the invert of the tunnel. What we saw in actuality was that those poorly graded gravels with cobbles and boulders, you can see a boulder on the left-hand photo, and then on the right-hand photo, you can see that those gravel layers actually extended all the way down to the invert of the tunnel. That's just fast raveling ground. So a pre-support system was definitely required due to the size of the tunnel during excavation before you could install the initial liner. And you can see in this photo here the lattice girders with the shotcrete, steel reinforced or fiber reinforced shotcrete as they are extending the bench, the top bench, and the lower benches. So the pre-support system with the pipe canopy included 27 canopy pipes or canopy tubes placed in a double row configuration between 10 and 2 o'clock. And the idea for that is that you choose any point along that 10 and 2 o'clock line, and you have a triangulation of at least 3 pipe canopy tubes that will help to support the ground and create that ground arching effect, that pre-support. The initial liner then was, as I said, lattice girders on 4-foot centers with 10 inches of fiber reinforced 5,000 psi shotcrete. And that was included with the pipe canopy pre-support. In our numerical model, we used Rock Science RS2, which many are familiar with. And you can see the pipe canopy, which was like a improved zone within the soil above, and then the lattice girder shotcrete. And we found the settlement at the surface, which is what the owner was really concerned about, was settlement of the road. And that was at 0.02 of a foot. And then the final liner was also designed using a double mat number 4 bar with 9 inches of shotcrete. This was done using a RISA structural modeling software. So for the construction of the pipe canopy itself, we actually welded a drilling template to the soldier piles. It's a soldier pile and lagging shaft, and you can see it there welded. And it just helped for the drillers to know exactly where to install the pipes. And as they installed that row of pipes, then they would bench down the shafts and install the next row of pipes. And this was done using a down the hole hammer, Atlas Copco Kilo 60 reverse circulation drill. Down the hole hammer was selected to install the pipes due to the gravel and cobbles and boulders that were expected along the drive. An auger boring system or horizontal directional drill was not as applicable due to the ground conditions. And even with using a down the hole hammer system and the template, we still had loss of lining grade on a few of the pipes. It wasn't anything major. There was minimal voids that were created between the pipes as they excavated, and some raveling of the ground that with a quick flash coat of shotcrete stopped any ground movement. And then the excavation was done in two headings using the sequential excavation method. And you had a top heading and then a bench heading. And the top was done using an articulated telescoping road header. And then you had a small excavator that benched out the bottom and took away all the muck. Once the initial support was installed, the floor slab was poured. That created a great working surface for the guys to install the scaffolding, then to install the PVC lined waterproofing membrane, as well as the double mat support for the final liner. And we also, Kilduff did ground monitoring and roadway settlements using surface arrays, 5-point surface arrays. And we also did deep settlement monitoring points and utility monitoring points. The deep settlement monitoring points were just rebar stuck about 10 feet into the ground, augured into place with concrete to check near the crown of the tunnel for excess movement as well. And the graph I'm showing you down here on the left is for the 5 roadway arrays consisting of five prisms each. That's the roadway prisms look like what you can see there in the left photo. And we used our threshold value and shutdown values that had been given to us by the owner. Again, if you remember back, we had modeled this surface settlement at 0.02 of a foot. And as you can see, the arrays stayed below that 0.02 of a foot movement and only got to about 0.015 feet of movement. So our model is actually a bit conservative. So this project was completed on time and on budget. The pipe canopy proved to be the correct approach given the ground conditions in the low cover and the minimal ground movement at the surface that we saw. And if anything would have been changed about the design, which I feel like people should be more open about that with presentations, is we would have gone with the larger pipes because of loss of line and grade when we hit some of those cobbles and boulders. That caused line and grade movement with the pipes. Whereas if we would have gone with the 24-inch pipe, it's easier to keep the pipes on line and grade. So the second project we're going to look at quickly is a Mapleton tunnel. It's a pedestrian tunnel, about 100 linear feet in length. And this tunnel is only 10 feet below two active Union Pacific Railroad tracks. The tunnel is 16 feet by 12 feet outside diameter, and the final diameter of 14 feet by 10 feet. So again, you are less than one diameter from the crown of the tunnel to the surface. And you're going to have active railroad tracks that you're tunneling under. So this necessitated some sort of pre-support system. And we decided to go with the pipe canopy system again. In this case, the pipe canopy as well as the tunnel will be excavated mainly through sandy silt up above near the crown, and then more of a silty gravel below. So the soil itself, the ground conditions weren't as much of an issue with this tunnel. It's more of the low cover and the railroad tracks that are requiring this pre-support method. So we beefed up the pipe canopy tubes to be 2 feet or 24 inches in diameter, and there's 16 canopy tubes coming down all the way down the sides. And the owner required a rectangular shape for this tunnel, being a pedestrian tunnel and needing the room for people to get underneath the railroad tracks. And we are planning to grout within and outside of these pipes. So the idea is to install perforated steel casing in this case, and then you can actually contact grout outside of the pipes and create much more of a strong supported surface and reinforced ground all the way around the tunnel itself. So the initial excavation and support was modeled in RS2 again with an improved zone, which is shown in the blue. And then you have your excavation. And the initial support in this case is designed to be steel sets on 4-foot centers with 6 inches of fiber reinforced shotcrete, and then a 6-inch thick concrete invert to stop any basal instability or heave from the bottom. And then the final support is just an additional 5 inches of reinforced shotcrete over the initial shotcrete and steel sets, and then an additional 6 inches concrete invert slab for finished grade. Also, settlement monitoring will need to occur on the railroad tracks during this tunnel crossing. So the idea is to do 7-point rail settlement arrays, and then 2 deep settlement points like we had at North Temple, and then 10 surface monitoring points along the braced excavation in the shafts near the railroads themselves. And Union Pacific has extremely tight tolerances for what their railroads can see in terms of movement. So the pre-support system needs to be designed and shown to improve with numerical modeling that you can stay under their requirements. So this project is currently still in design. We're at about 60% design, and we're waiting some more geotech before we can move forward with the final stages of the design. So I don't have any construction photos to show you, unfortunately. Hopefully I can be back with this completed and we can go through it again. But we chose the 24-inch concrete filled steel casings due to the robustness of that system and the strong pre-support to essentially all the surcharge loading from above and support all the surcharge loading. And it addresses the cobbles and boulders and the ground conditions that we might encounter along the drive, being in a river valley system here. This is in south of Utah. So just to wrap everything up that we talked about, pipe canopies are a proven method for pre-support, and we are trying to push this into the industry and the market here in the States, and it can solve very specific issues within then tunneling alignments where you have disruption to the ground surface and you're trying to avoid that because of minimal cover. And then also where you have very poor ground conditions with running and raveling ground, where the SEM method alone might not be enough to give you the stand up time required to install your initial support. And in both the case studies that we looked at, the adverse ground conditions and low cover and sensitive structures necessitated the need for the pipe canopy pre-support. And with that, I'd like to open this up to any questions that people have. No questions? Okay. Well, thank you all for coming. There's no other questions. I don't think we need to stay on. So, yeah, everybody have a good day.
Thank you.
Thank you.